evidence is mounting in one particular area, and people are looking into it, which is the actual expansion rate itself. There's a tension between the expansion rate measured locally and the expansion rate you infer when you study the cosmic microwave background. It's known as the Hubble tension. And so people are trying to say, okay, maybe it's due to an issue with the observations, and plenty of people are working on that. And as time goes by, that has not yet been a conclusive answer. So people are trying to say, okay, how could I actually alter our best idea of how the universe works to accommodate that?
There's been a lot of data recently that's coming out of the new space telescope, which suggests that there are galaxies at the very, very edge of the universe that are fully formed much earlier than we would expect. We're talking about maybe, as we'll get into the conversation, galaxies that are the size of the Milky Way that appear to have formed in the first 500 million years of the entire history of the universe.
Which is like a little more than twice the age of the bed of the oceans on Earth. So you're talking about not only an Earth forming, but like stars and everything forming in an unbelievably short amount of time. And this has obviously made headlines lately. There's some talk of different cosmologists scrambling to repair the basic relativistic equations in a way that accounts for this, dark energy solutions and everything else, modified gravity. And so it may be the case that this does need to be examined. Dr. Finkelstein, who's on the show today, reminds us that the calibrations aren't finished, so we'll need 6 months to actually be able to make any conclusions for sure about those redshifts.
And he gives us the opportunity to talk about the conventional wisdom, the reasons why the theories that are currently in place today are so firmly in place. And that's something that I spend a lot of time thinking about, because my nature is to look at the fundamental building blocks and to try to understand what is wrong with the fundamental building blocks. And it seems like that's not really something that's happening in cosmology today. And so it was really, really good to be able to drill down to the basis of why there isn't curiosity about this. And I think that a big goal of the podcast is to figure out what it would take to get these ideas looked at again. And in order to do that, we have to talk to the people who are representatives of these fundamental ideas and to hear their perspectives on why these things are so foundational and immovable. And I think that Professor Finkelstein really offered us a lot of insight onto the field. He offered us a lot of insight into the things that are maybe going to change, maybe not going to change. And he had a lot of really, really interesting things to tell us about the actual process of observing and how telescopes work and what it takes to be able to understand something that you get out of the telescope.
And what it takes to shift a paradigm.
All very cool.
That's an interesting point that's been coming up on the show a lot, is scientists seem to be open to the fact that paradigm shifts do happen, but it's not an easy process. And so getting each scientist's take on what it would take in their field is really quite fascinating. I don't want to give it away because he's going to get into that in a minute.
And I think that something that's really worth paying attention to is that many of the theories that have proposed to be a paradigm shift in cosmology over the course of the last 50 years or so have big problems. It's not like there's some one theory that has been proposed that can perfectly replace all of the observations, right? You can't put a new theory down if you're going to break something else down the line. You have to have a theory that's able to account for everything. And that's a huge challenge. And the better that we can understand what changing the theory will break and how the old theories have been discredited or what are the points that prevent them from being accepted widely, the better that we will be at understanding what deserves to stand the test of time and what deserves to perhaps shift.
So this is really important, and we need to talk to more people who are inside the academy studying this and really understand what their arguments are so that we can understand what needs to change. And that's what you guys are really interested in. That's why you're here. I think things do change. They inevitably will. If we had stuck with Newton's theory of gravity, we'd be making even crazier insinuations, perhaps in the Big Bang, because if you extrapolate things out too far, you run into madness. with any mathematical theory.
And so if you like the podcast, give it a like, comment, subscribe, tell your friends, share it with people. Growing our audience is the absolute best thing that we can do. And that is how you can help without spending any money or putting any skin in the game beyond just vouching for us. If you've already done that and you really love what we do, please support us on Patreon. We are not making very much money off of this right now. And we have such big visions of all of the things that we want to do.
All the money goes back into the show. We're literally spending every dime on this. And I really think that if we get a little bit more patronage, we can start releasing more episodes and get some help with the editing, which would be awesome.
We might be able to finally break away from Zoom and go see people in person so that everything isn't through this digital screen. We want to be able to get people together in person and be able to have big talks and conferences and really push the boundaries. We want to bring together the people that have well-developed ideas that fall outside of what the Academy accepts, and we want to bring together the greatest minds of the Academy, and we want to help shift the paradigm forward into a better future for science. And you can help that happen by supporting us on Patreon.
Telling your friends, growing the audience. That's the first thing that guests look at when we invite them to the shows. Like, how many people are watching this, right? That's what people care about. So share this with people. Let's build this subscriber base. Let's actually be able to have a huge base here where we can bring in very important people and get them to talk.
And get them to talk, but also force them to look at these ideas that maybe they don't have to look at otherwise.
The scientific revolution starts now.
Deep is the Science Joy Podcast.
Let us see in the dark.
Is the red shirt in honor of the redshift?
We could pretend that I thought that far ahead, yes. And it's not just the first one I saw in my closet this morning.
As an astronomer, do you find yourself informing your clothes choices with your astronomical observations, or it's...
Almost never. Almost never, no. Usually it's based on how warm and humid it is outside in Texas. And today, medium warm, very humid. So Under Armour polo, it is.
You're in Austin?
Mm-hmm. Yeah.
Austin to me is the equivalent of a different planet. I've heard of it, but I have no idea what it's like.
It's wonderful, like culturally. Weather-wise, it's very hot a lot and getting drier with climate change. So, a typical summer day these days is like 100 degrees and like not too humid, but not nearly as dry as Arizona. I think more in the past, it used to be a little cooler, like 90, 95 and more humid. So it's sort of trending towards Tucson-like.
Yeah,
it's been raining lately, so it's been cooler, but more humid. Not necessarily more comfortable.
We could go for some of that rain.
Yeah.
Where are you all at?
We're stuck in the middle of the forest fires out here on the West Coast. We're on the border of California and Oregon.
Oh, cool. I have driven past that border many a time.
It's quite beautiful, except sometimes it burns really badly. Lately, especially.
In Wairika, once upon a road trip.
Yeah,
Wairika is better than Eureka. We were in Eureka the other day, and it has the feeling of a town that knows that it's about to be swept off into the ocean, and so it's just kind of accepted its fate. And it's just like, what happens.
Yeah.
Because
it's a beautiful part of the country, forest fires, notwithstanding.
Yeah. I mean, it's really interesting to live on the West Coast because we live under threat of annihilation, and forest fires are just the most recent phenomenon. But, you drive down the coast and there's all this evidence of unbelievable tsunamis.
Because they pretty regularly too.
I think every 300 years or so. 500 years, and it's been about 300 years since the last one. And so you drive down the coast and you're just like, well, that's spooky.
Why are there no animals?
Why are there no animals here? And it's perfectly flat for like a mile inland.
Yeah, I grew up in Seattle, so I'm very familiar with fear of like annihilation by earthquake at any time.
Well, like in Seattle, you have Rainier too, which is just the sentinel that just is beautiful, but threatens like an angry god to wipe you off the map.
I lived on a hill, so on a plateau, so we were safe. We were out of the range. My parents have since moved closer. They claim they're still safe. There's a big canyon in between them and the mountain. So if it did erupt in their general direction, they claim they would still be fine, but we'll see.
Oh, that's funny. I mean, I think that that's just kind of the human condition to live with the constant threat of annihilation and just to be like, you know, it probably won't happen to me. It's probably going to happen to somebody else.
Yeah, you kind of have to live.
Yeah, we're all gonna die, so that's pretty much guaranteed.
I don't.
Annihilation must occur.
Excuse me. I plan to live forever.
Good luck.
Transhumanism all the way.
Good luck. So what have you been working on lately? So we found out about you because at one point, I'm not sure if it's the case anymore, but you had the record for the oldest galaxy on record, which is pretty awesome.
Yeah, like the recent JWST discovery. Because we had a record like 10 years ago, but more recently, I don't think we ever actually held it. Not that we don't have like a championship belt or anything we pass around. We should. It was. Our paper was submitted on the same day as a few others, all sort of probing this very early universe time.
Gotcha.
But yeah, that's still what we've been working on, getting to know the data better. It is challenging. We're used to data from the Hubble Space Telescope that are very well calibrated, very well understood. You can take your pictures, you can do your measurements, you know exactly what you need to do and do whatever analysis it is you want to do. It's been more challenging here.
Can you walk us through a little bit of the nitty gritties of what that means to take a new telescope up to actual trustworthy operational capacity? Or?
Yeah, so I'll give you one most important example, and then one that we've been spending way too much time with. So the most important example is what we would call flux calibration. So when you take a picture with a telescope, we don't look through these telescopes anymore. It's in space, so we can't anyways. So we have a digital camera, essentially. It's on the telescope. You download it to your computer. You look at it, and you can measure in every pixel in your image. There's a number, and that number corresponds to some. What we want to know is what is the physical flux, like how many photons per second does that number correspond to? But that's tricky because what happens is photons hit the detector, and depending on the different technology, different things happen, but that basically gets converted into a digital number. But not every photon hits the detector because there are reflections off of mirrors, there are transmissions through lenses, and every time you bounce light, you lose a little bit. And so the way we go from a number to like a real physical flux or a true number of photons is we observe something that we know the brightness of. So a star, usually, that's been very well studied. We've calibrated it from multiple different telescopes. You know exactly how bright that star is at every different wavelength.
Are these the standard candles?
They are similar. It's a type of standard candle.
Gotcha.
Yeah. So we call them standard stars.
Standard stars.
And what you need to do is observe them, put them, ideally you would put them on like every single pixel. That's like way overkill, but you still want to put them at all the different regions of your detector, your camera. Probably observe them at different times to make sure nothing's changing with time. And so that's a like year-long process that's happening through the first year of operations.
You have to like check every single piece of the CMOS chip, basically, whatever it is.
Yeah, ideally you would want to, yes.
I see.
So when the first images came out, the calibration files that came with it, so there's basically a file that says, here's how you convert the data value to a number of photons, were actually based on ground-based measurements. So while the telescope was on the ground sitting in a lab, they took observations of like, some kind of lamp that they knew the brightness of. And that's fine. That's better than nothing. But as you might expect, once the telescope goes up into space, things can change. And they have. And so a couple weeks ago, they released a new calibration file that was based on space-based observations of a standard star, but not nearly the number of observations, the level of observations you might want to get everything perfectly right, but it still improved things.
Do you mean that things can change because the conditions are different, or it jiggles around in the spaceship, or
yeah, it's like some of that possibly, but more importantly is we need to understand the response of every part of the array of the detector, and that hasn't been done yet.
But if you check it on the ground and you have checked all parts of the array, what is the shift that happens once you get it into space?
Right. So that could be things changing on launch. I would guess probably that's not a big part of it, but I would guess the ground-based observations were probably multiple years ago. And the sensitivity of these detectors can change with time. The efficiency of reflections can change with time. So yeah, so certainly a time component. And in space, you're absolutely in a vacuum, and you can put things in a vacuum chamber. They did put Webb in a vacuum chamber on the ground. I don't know the details of how they did these calibrations on the ground, but it's possible the environment could play some effect, or maybe not. I'm not sure.
Where's this thing sitting at right now?
That's a good question.
It is 1 million miles away at a point in space called the second Lagrange point. You can imagine if you have the sun here, the Earth orbits around the sun. JWST is 1 million miles away from the Earth in the opposite direction of the sun.
Nice.
And the reason why it's there is it has this big sun shield, this big sort of shade, if you will, that you can see there, multi-layer shade. And it goes there so it can put the Earth, the moon, and the sun all on the other side of the sunshade and block the light from all three of those objects.
That makes sense.
And if it was in Earth orbit, it could not. It could not do that. The Earth is very bright in the infrared, and this is infrared telescope, so we need to get it pretty far away from the Earth. Not too far away, though, because we need to be able to download data from it pretty quickly. So
what
is important.
I'm sorry. What I was going to say, what are the biggest changes from the last generation? Was it the Hubble that was the main telescope prior to this? What's different about this?
Yeah, so Hubble is certainly the one most people think of. There have been lots of space telescopes, often looking at different wavelengths, like there are X-ray telescopes, other infrared telescopes, millimeter wavelength telescopes, radio telescopes. But Hubble is certainly the most famous one. I think it was one of the first. It's also a visible wavelength telescope, so we can see things at the same colors that our eyes see. So the biggest changes, biggest advances, the mirror is much larger. So the diameter of JWST's mirror is 6.5 meters, whereas Hubble was 2.4 meters. So the difference in area is about 7. So imagine you have telescopes like big light buckets. So if you wanted to catch rainwater, you'd rather use a bigger bucket than a smaller bucket. Same thing with telescopes. Bigger buckets cost more money. So that's why it takes a while to build things bigger and bigger. So that's the biggest advantage. And then JWST is also optimized for infrared light as opposed to visible wavelength light. So it looks a little bit redder than our eyes can see.
And so why optimize for infrared?
A variety of reasons. Number one science case of JWST is to search for the earliest galaxies in the universe. And because the universe is expanding, that's carrying all galaxies away from us. And as things move away from you, their light gets shifted to redder colors. And the farther away they are, the faster they're moving away from you, and the more redder their light gets shifted, which is this term redshift, which you had alluded to earlier.
Yeah, I want to talk about redshifts in a second, but I still want to understand this telescope a bit better. Why do they use mirrored telescopes? Because we have a mirrored telescope too, and from what I understand, there's some problems with mirrored telescopes. Like you have sometimes the image quality can suffer compared to just a series of lenses. Is it a matter of saving space or?
Yeah, so a number of answers to that. Yes, so if you have a mirror, if you grind a mirror in a particular shape, you can definitely have different kinds of aberrations. This was very famously a flaw with Hubble. There was an aberration in its mirror that they didn't catch on the ground. And they were able to fix it with essentially a lens. So now every observation with Hubble goes through a lens that removes that defect from the mirror. In space, it's a good answer, a good question. So on the ground, the first telescopes were lens telescopes. But when you're using a lens, you're passing light through the lens and capturing light over a big area and bringing it to a focus. But that means you can't support the lens from underneath, or you block the light. And when you get to a lens that's bigger than about a meter, gravity actually distorts the lens. It can no longer keep its rigid shape. And you could fix that by holding it from underneath, but then you're blocking the light. Whereas a mirror, you can support it fully underneath and you don't have that problem. And mirrors are just, if not, I think, more efficient reflectors than lenses are transmitters. And so I think that is primarily why we're going to use mirrors in space. We do use mirrors in space. But I'm more familiar with the argument on the ground. You simply can't build a lens telescope that's bigger than about a meter in diameter.
That's really interesting. Yeah. I guess technically glass is some sort of a amorphous, viscous, solid thing. It does drip, I guess. There's these old cathedrals where the glass is kind of piled up at the bottom of it.
Well, and I would wonder how big of a lens you would need to have the same magnification power as a mirror, right? It seems like you would need a much larger lens. And I don't know if that's intuitively correct or not.
No, yeah. So it should be Basically, the diameter is the main thing. It's how much light are you gathering? Because light from a distant galaxy, from a star, whatever, it's hitting all over the Earth. You can think of a star as sending light off in all directions from that star's surface. And so the more of that light you gather, the better you can see that object.
Mm-mm.
So that's why mirror size is so important, because that light is hitting all over the place. It's being wasted unless you're capturing it in your mirror or in your lens.
I seem to remember something about the lenses having increased chromatic aberrations as well. I don't know if that's the case with the large ones.
You might be right. You might be right. You're bringing up things that I certainly learned in graduate school that I haven't studied as much recently.
Yeah.
Certainly, both mirrors and lenses can have defects. Mirrors, I think, are a bit easier to handle.
Yeah, the only reason I know about it is
bouncing the light instead of transmitting the light through a medium.
Yeah, that makes sense. My buddy just lent us a telescope, and it's one of these mirrored ones, and we've been having a heck of a time getting it working. But we did get some decent images of some decent views of Jupiter and its moons the other night, and
nice.
We saw Saturn's ring, which is pretty cool.
There's still something that's not quite right about it, though. There's like a certain amount of blur, and I can't tell if it's because the lenses, the actual magnification lenses, are still dirty. And so I can't even imagine how difficult it is to maintain something that is off planet. Is it something that needs to be cleaned? Is there dust that settles on it? Is there?
Yeah.
How does that work?
So certainly on the ground, that's a big part of ground-based telescope operations. Is you have to clean the mirrors and re-illuminize the mirrors. I was just at McDonald Observatory in West Texas, and they showed me various insect stuff that gets on the telescope and actually eats away at the aluminum coating. And so you can see sort of these holes in the aluminum, and that's one of the many things that happen. You have to re-illuminize. In space, no insects, no dirt. There is cosmic dust out there, tiny little grains of heavy elements. Those are not going to settle on the telescope so much. What we're more worried about is impacts, so micrometeorite impacts. And you can't avoid it. There's lots of rocks in space. They're usually pretty small, but they're moving incredibly quickly. So even a small rock can cause a problem. And there actually was a larger than expected micrometeorite impact 3 or 4 months ago on JWST. And there were some news articles about this, and it affected the mirror in a fairly minor way. And this is something that will just over the lifetime of the telescope degrade the performance. And so it was known that this would happen. It just so happened that they got kind of a big one pretty early on, but it was not too detrimental.
I'm surprised that the solar wind isn't more corrosive. Is it because it's got a shield, or?
So that is a good. You guys asked lots of questions I never thought about. So certainly the sun shield is blocking all of the light from the sun. The solar wind is charged particles, not light. I have to think that those are even easier to block than light. But I admit I don't know for sure.
But there's like cosmic radiation and stuff. Is that blocked? Mm-hmm. Is that part of what's being blocked by the sun shield?
No, because cosmic radiation is coming from everywhere. So there are particular particles called cosmic rays, which are very rapidly traveling nuclei of atoms. They can come from supernovae explosions. They come from all over the place. And they don't get blocked. They hit the detector. And so when you look at a raw image from the telescope, you could actually see cosmic rays, hits, like little bright spots. The interesting thing about the way that detector technology works is, unlike a visible wavelength camera where you kind of open a shutter, gather your light, and then close the shutter, the near-infrared detectors are constantly recording how much light basically is being collected by every pixel. And so for an astrophysical source, you would expect sort of a slow ramp up of the amount of light you're receiving, because you're getting a little bit of light every second, right? And so when a cosmic ray hits, you'll have like a slow ramp up and then a huge jump, and then that ramp will resume. And so the way you make the image, we call it reading up the ramp. So you take your observation and you can sort of tell the camera how often you want it to read. So maybe you have 20, 30, 40 data points, and you basically fit a line to the light that's being received. And you can actually remove the effects of cosmic rays in that way.
Interesting.
Smart.
Unless they're really big, or unless they hit very early, then that sort of blast that pixel very early in the observation, and you don't really know how much light was there. And so we can't completely get rid of them, but you can mitigate them pretty well.
No, when we're looking through our telescope on Earth, we're constantly having to track the stars, right? Obviously, because the Earth is, our platform is spinning.
Mhm.
How does the telescope stay pointed at one place, or does it have a does it move? Or
I would assume that the motion of the L2 would be so slow
is it really
as
slow?
to
It doesn't
be
matter.
imperceptible.
So it's orbiting the sun with the Earth, so it's still moving. So we have to keep the telescope pointed at a particular place. And it has an instrument called a fine guidance sensor. And so when you go to start an observation, then this is all sort of pre-planned. You find a nearby star to your target that will fall in this camera, the fine guidance sensor. And you say, okay, if I have my target right in its camera, viewer, I should see this star at this pixel in the fine guidance sensor. And so I'm going to move the telescope so the star falls in the right place. And then I'm going to continuously monitor that fine guidance sensor and keep that star at that pixel, making any very tiny motions of the telescope, but making any small corrections as needed.
And is it like swivel, or is it does it use thrusters, or does it just swivel its head? Or?
So it's a good question. I've been meaning to look up. I'm like 99% sure it uses gyroscopic reaction wheels because that's what Hubble used. But I should look it up in real time while we're talking here because I've been asked that question enough.
So it's like an inertial based thing of some sort. Interesting.
Yeah. So Hubble had 6 gyros, and I think it's down to 3 at this point. 3 of them have broken.
Oh no.
And it's just, time goes by and it's not getting serviced anymore.
Yeah. What's the plan with that? Are they gonna just crash it into the ocean, or?
Its orbit will eventually degrade and it will crash somewhere. Unknown.
Hopefully not New York City, or hopefully not Austin, or
it's actually pretty small. I think it will like fully burn up in the atmosphere. It's the size of a school bus, but still pretty small.
It seems like such a tragedy to not find a way to be able to bring it down and have it as a museum piece somewhere.
If we still had a space shuttle, we could do that. Space shuttle is what carried it up into space. It could bring it back, but we don't have a space shuttle.
Is anybody vying for something to replace the space shuttle?
Artemis. Have you heard about Artemis? It was big news on Tuesday because it was supposed to launch. It's NASA's next launch system. So there was going to be basically its first ever launch. It was going to be an uncrewed mission.
It's like a rocket though, right? It's more like a Saturn V type.
Similar, yep, more powerful, but similar in sort of style. Put the humans in the little capsule at the top. So that is our next. That is NASA's main way to put people in space. And now they're going to try and launch it on Saturday. So hopefully it will work out then. I did just learn today that while it's in space, it communicates with the ground with the same array of radio antennae called the Deep Space Network that JWST uses. And there will be periods of time, like that mission has priority, that JWST won't be able to talk to the ground.
Oh, no.
So I found that pretty interesting. So that actually have to alter the JWST science schedule to make sure you don't want to take a bunch of observations and not be able to download them. Then you're just sitting there waiting. So
that's really interesting. Got to share the comms.
It reminds me of dial-up a little bit, like somebody's on the phone and you have to wait before you can connect to the internet. How much? So does it have a lot of storage space? Does it have a hard drive?
Not. So it has a hard drive. But an interesting thing about lots of things with NASA is the technology all gets locked in years before it launches. So
it's got like a 200 megabyte hard drive.
Your phone, like my phone, no, but like gigabyte. I think it's either 64 or 128 gigabytes.
Wow, that's unreal.
So it's small, right? And of course they don't want it to fill up. So usually once it gets above like 32, above half, I think it's 64 because I remember seeing 32 is halfway, then it really needs to download it.
That's
and
incredible.
It downloads pretty slow. So you have to keep an eye on that. It was a similar issue with Hubble, and Hubble's space was even smaller than that.
How big is a single image?
Depends. Hundreds of megabytes. Wow. It depends on the camera and a variety of things, but on the order of hundreds of megabytes. So you can't take a ton of data. So it needs to download basically every day. So with Hubble, Hubble's going around the Earth. And so part of the time it's on the side of the Earth the sun is, and you're not doing any science. And so it can download then, right? Whereas Webb doesn't have that problem. So in principle, it can observe all the time, but you need to make sure you're downloading the data at a fast enough rate that you don't fill up the hard drive.
That's fascinating.
That is fascinating. Yeah, I think my laptop's got that one beat, actually.
Just barely. Mine is just barely above that. What's the observing schedule like? Because I hear people constantly complaining about Earth-based telescopes of how hard it is to get time. And there's a lot of Earth-based telescopes, so I imagine that if you have just this one, that it's not an easy schedule to get onto.
So it's not easy. The proposals for the first year of operations, they were due in November of 2020, and we call it the oversubscription rate. So like the total amount of time people asked for divided by the amount that was available was a factor of 3.8 to 1. So you sort of had like a 25% chance of getting time, which is not that bad.
Yeah, I thought it would be worse.
Yeah.
10 to 1. But I can already tell you it will definitely be worse in cycle 2, because what happens is there are lots of good ideas. Most of them don't get on the telescope because there's only one telescope. But a year later, that's still a good idea. So you're going to take that proposal and you're going to resubmit it, maybe spend a bit of time updating it. But you'll also probably come up with a new idea and write that proposal.
Yeah, like what are the promising candidate ideas that, like, what does it look like to write a proposal for I want to look at something? Like, how do you justify looking at it?
Yeah.
What's that look like? You propose that it might modify some theory, or
is it enough to just be like, I don't know, it's
seems
cool.
Yeah, I don't know.
No. If you're like at a university that has its own telescope and it has lots of time and it's non-competitive, then sure, you can write, hey, I should do this because it might be interesting. But with something like JWST, it has to be incredibly compelling. So you have to have like an amazing science case. Here is this problem that I can solve with these observations. And then you have to prove that you need this specific telescope, because this is a very finite competitive resource. If you could do it with a ground-based 4-meter telescope, you should never be doing it with JWST.
Can you give us an example of a problem that would,
Yeah, I will tell you. So the image behind me that comes from our Sears early release science program, we wanted to study the first, galaxies forming in the first 500 million years of cosmic time. So to do that, you need to observe at infrared wavelengths, and they're very faint, so you need a big telescope. And so literally the only telescope that can do that is JWST. And that's basically why it was built. That's the number one science case for JWST, is to study these really early universe galaxies. So it's a pretty easy case to make, but of course, that's not a secret. So many people are writing proposals making that same case, and you have to try to make yours the most compelling in some way.
3 to 1 doesn't seem too intimidating.
It's almost 4 to 1, 3.8.
Almost either way. Even 10 to 1 seems not that bad compared to writing some grants.
Which is,
like if you're a basic biologist or something. My question is, are there only 3 to 1? Is that there aren't that many people that are trained in working with this kind of telescope? Like, what does it take to be prepared?
Or are
for that?
there are not that many people that are trying to look at super early galaxies?
Yeah, so the telescope, that's just one of the science cases, looking inside star-forming regions in our galaxy, studying the atmospheres of exoplanets there. You can use it for just about anything. There are, I don't know, astronomers around the world probably number in the tens of thousands. So there's, not as many as biologists, but there's a lot of people. And NASA made a big point of trying to train people to use this telescope. So they ran tons of webinars, conferences, tons of training materials online. So many people could write a proposal. And the other thing to think about, 3.8 to 1 isn't too bad. I bet in the next cycle that will double. I bet it's like 7 or 8 to 1. The process of writing a good proposal is like at least a month of your life. In our early release science program that we have now, we took 10 months to write. And so it's a huge investment of your time for a sort of small chance of success.
You've mentioned the early release science program twice now. What is it?
Yeah, so it's the name of it is SEERS, the Cosmic Evolution Early Release Science Survey. And it's one of 13 programs that were selected by NASA to be executed early in the JWST mission. And they sort of span all areas of astronomy. So you probably saw this beautiful image of Jupiter about a week ago from the Solar System Early Release Science Program. We are the other end. We are the Early Universe Early Release Science Program. And we're taking one area of the sky and observing it with a bunch of JWST's different cameras. And so the image behind my head comes from NIRCam, which is sort of the workhorse near-infrared camera. And this is the image where we found Maisie's galaxy, named after my daughter, that really early universe galaxy. Lots of other things we're finding that image. But in December, we'll get more imaging, but we'll also do spectra. So we'll be able to take light from a lot of these galaxies and split it apart into its component colors, learn in detail what these galaxies are made out of.
Something that I've always wondered about these huge publicly funded science projects is why there isn't more of a citizen science initiative. Like, obviously,
I think there was for a little while.
like
Somebody was telling us.
like
that
somebody could just get onto Hubble off
maybe
the
not
street.
Hubble, but some of the bigger university scopes had. NASA had an initiative for a while. I think it might have been in the 90s where they opened up some portion of their time to citizen observers.
But I mean, there's so recently, I don't know if you saw this, but the federal government required that by 2026, all publicly funded research becomes immediately available for free, which is, you know, it's really a tragedy that Aaron Swartz didn't live to see this, because it's an incredible step that for somebody who doesn't have an institutional email address anymore, it basically the entire realm of scientific knowledge is closed to you unless you're willing to use the well-established but illegal workarounds.
It's not so bad in physics because they have these preprint servers.
That's true, but physics, I'm afraid, is only but one of the
Only
sciences.
but one, yeah.
Yeah, we do the same thing in astronomy, actually the same server as physics.
But so the question here is, why isn't there some small fraction of time where the public can write proposals and be able to get onto a publicly funded telescope? They've paid for it. We've paid for it.
So several answers to that question. So the first one I will say is that in my field, it's becoming more and more common, if not mandated, depending on the telescope, for the data to be public immediately. So this early release science survey behind me, the second the data were taken, anybody in the world could go download it. You don't need to have a university affiliation.
That's cool.
You might not know what to do with it if you're not trained.
Yeah.
That's sort of a different question. But a lot of the data from the first year of operations of the telescope are public like this, immediately public.
Are there training programs where because you said that NASA really trained people to be able to use the telescope and the data, are those webinars public where if somebody really, really wants to do it from outside the institution, they can figure it out?
Yeah, absolutely. I mean, those were, obviously targeted at scientists and at universities and research institutes, but they're on the internet, so it's all public. Anybody can download it. And there are citizen science projects. So we're doing one in Sears ourselves with the website Zooniverse, where you have something, lots of things that need looking at, and it's pretty easy to train somebody who's not an expert in a particular topic. And so we've done that a lot with galaxy morphology, so shapes of galaxies, classifying them into different categories. As for, why can't somebody from the general public just get on the telescope? It's really something I've never thought of before, but like my initial gut reaction is it takes years and years and years of training to be an astronomer. And even then, there are way too many good ideas than there is time in a year on the telescope. And the likelihood that a non-astronomer is going to come up with an idea that like adds value and really uses the telescope in the way it should be used and, worth the money of that time is like very unlikely. That's what I would guess. But NASA has a huge public engagement component of what it does. And so that's where the paying back society part of it comes in. It's not that everybody should get, a piece of the telescope because they paid for it, but they certainly should understand what it is, where it is, what it's doing, and what's being found out from it.
I think that you're right that a lot of people probably aren't as highly trained as somebody who's a professional astronomer, but surfing through, we do a science podcast. You would be absolutely shocked by the number of incredibly well-trained nerds that have, simply due to their absurd love of science and their dedication to whatever their interest is, have read everything, have developed a deep understanding of some field that they're not necessarily a part of traditionally. And so, sure, that most people, I think, probably would write a proposal that's just kind of, but I guarantee you that there are amateurs outside of the academy that have fantastic ideas. And I would love to see a path for people that are amateurs to be able to have access to something like this, because there's a huge tension between people who work outside the academy and those who work inside the academy. And I don't think that tension is good. What were you going to say?
I was just gonna say I'd be more afraid of some amateur like breaking the telescope or something.
It's
I mean,
true,
if
it's
they're
true.
literally moving the lens around every time they have to calibrate it to some standard star, and it just seems like things could go sideways. You could misalign something. Or
You could have like a training program where you
Yeah,
put
of
them on
course,
like
of course, of course.
progressively larger, like you could have like a pipeline where it's
that's
right.
what I'd be afraid of if I was
Yeah,
in charge.
that's true. That's true.
Like, don't touch my telescope.
So I was looking this up while you were talking because I suspected that probably you don't have to be affiliated with the university, and that is correct. You don't. And
That's cool.
specifically, the call for proposal says investigators of any nationality or affiliation may submit and be included on JWST proposals. So tell your well-trained
Yeah,
nerds
hear that,
their
nerds?
ideas.
That is
My lovely
amazing.
nerds, get out there, write proposals.
And I say
after it.
nerds with utmost love and include myself among you, so don't take it personally. That's incredible. So it's, then you get into the secondary question of would a proposal by somebody who's not academically affiliated be selected, but at the very least, the fact that it's there and publicly stated that it's open.
Well, all proposals now by NASA and soon basically everywhere are double-blind anonymous. So that means the proposal writers don't know who's reviewing it, and the reviewers don't know who wrote it
Or the affiliation.
or the affiliation.
That's pretty cool.
That's very cool.
That's really cool.
Well, welcome to the new era of democratic science. I love that.
However, there is the problem still remains that the reviewers are probably interested in some group of topics, right?
And I mean, you see this a lot. So there's, I don't know if do you know the writing of, I think it's Halton Arp? So Halton Arp was an astrophysicist, I guess astronomer, and he wrote this book called Seeing Red, where he was...
No, I'm sorry. I do know. I didn't know Arp's first name, but yes, Arp is famous.
What's
older
your...
astronomer.
I think he worked under Hubble.
Yeah, I think that he was trained, but he was one of the last people to be trained by Hubble.
He has a galaxy. He had a galaxy catalog and has galaxies like Arp 220 is like a famous one of his galaxies.
Yeah, I think there's the Atlas of Unusual Galaxies or something like that.
There it is, Atlas of Peculiar Galaxies.
There we go. And something else that he was really particularly focused on is he was like, hey, there's a bunch of objects that have anomalous redshifts. Like he was, I think that one of the things that he was really looking at was galactic clusters that appear to have quasars that have been ejected from them that have redshifts that are higher than the galaxies that they appear to be ejected from. And he was, in his book, right in the first chapter, he writes about the fact that many people had attempted to request to look at that galaxy. And proposals were continuously disparaged and rejected until Margaret Burbridge actually came through. And this was at the end of her illustrious 50-year career, and she got onto a telescope, and she looked at it, and she wrote a paper that she ended up publishing about this anomalous redshift. But he has this particularly sharp axe to grind where he is insistent, or I guess was, he's not alive anymore, that there are a collection of objects that people will not look at because they're inconvenient.
Yeah, so I think your knowledge of astronomy history is better than mine. So Arp had this basically belief that quasars, which we now know are very luminous but very distant objects. It's light coming from a supermassive black hole in a galaxy that's actively accreting matter. And you can measure the redshift or the velocity of these objects, and they're very high. And so we interpret that now, and I think there is, universal agreement now that it's because they're very distant and moving away from us because the universe is expanding, because the started in the Big Bang and well-established theories today. He was convinced, I think it was him, that these quasars were actually not that distant and they had these high velocities because they were ejected from some other nearby galaxy at an insanely high velocity through a physical mechanism that, we don't know of. And so I think when they were first discovered, sure, all ideas are on the table. But over time, we've since, learned what these objects actually are.
And so that leads us to redshift, which I think is a really interesting topic because there is not the ability to put redshift in a laboratory and to ask, are there other possible reasons for redshift except for expansion?
There's also a number of things I do want to talk about redshifts, but there's a few other things that you gauge distance by, right? It's not just redshifts. There's these magnitude ideas. Can you tell us how you know how far away something is?
Yeah, I think that's a good question.
So it's it basically comes down to something called the distance ladder. So redshift is the extreme example. That's something we can use to measure distances across the entire universe, but it's all calibrated down to closer and closer and closer to home. So, for example, we can measure the distance very precisely to the moon by putting a mirror on the moon, which astronauts did, and we can bounce a laser back and forth between the moon and the Earth. We know how fast light travels. We can measure the distance. We can measure the distance to nearby stars with a technique known as parallax, which is as the Earth orbits around the sun, nearby stars will appear to move in the sky relative to background stars through the same effect as when you hold your finger in front of your face and blink your eyes back and forth, you see your finger appearing to move. And it's just simple geometry. It's been known since the time of ancient Greeks that you could do that. It just turns out that parallax angles are way too small to be seen with the naked eye. So you need a telescope to do that. And the latest, greatest one is Gaia, which right now is mapping the positions of millions and millions of stars in our galaxy. Beyond that, you get into something that you had alluded to before called standard candles. So they're objects, particular types of objects that always have the same intrinsic luminosity. And so when you measure how bright they appear to be, you know how far away they are based on how faint they are. It's equivalent to taking a light bulb of known wattage. If I have a 60-watt light bulb and I'm standing at some distance from you and you had some device to measure how much light you were receiving, you could actually calculate my distance because you know the intrinsic brightness of that light bulb. A variety of different kinds of standard candles. The ones that work across the greatest distance are known as type 1a supernovae. It's a particular type of exploding star that tends to always have roughly the same brightness.
And you know they're the same type of light bulb because they have the same spectra? Is it
exactly.
A spectral analysis?
Yep. Exactly. For that particular one, yes. So you could take a spectrum of that type of supernova and they have particular features. Another well-studied one, this is what Edwin Hubble used to discover that the universe was expanding, is known as the period luminosity relation of Cepheids. So a Cepheid is a type of star that's variable. The star actually pulsates, and as it gets bigger, it gets brighter. As it gets smaller, it gets dimmer. And the period of pulsation is actually proportional to the average luminosity. And so Cepheid stars that are brighter have longer periods. And so if you look at a galaxy and you just take a bunch of images over, a period of hours, you can find stars that are varying. Okay, you can pick out which ones are Cepheids, that are a particular type of variable, and you measure their period, and that tells you what their luminosity is. And then you measure how bright they appear to be, and now you know the distance to all of those Cepheids. Say you find 20 in a galaxy, you would take the average of those, and that would tell you the distance between, Earth and that galaxy, essentially. It turned out in Hubble's time, the calibration of that relation was off. So Hubble's measurement of the expansion rate of the universe was actually way too big. And so we have since well calibrated that relationship.
Hubble, to the end of his life, was not certain that redshift implied expansion. He was always like, yo, maybe, but maybe not. And it seems like that's kind of the thing that I spend a lot of time.
Well, it was the priest Lemaitre that jumped on it more than anybody, I think. Originally. The Hubble relationship was well established, but somebody else came along
and
put a story
interpreted
to
it. Yeah, and that's kind of the story of science, right? You measure data, and then you have this data, and you have to come up with a story. And it's really important to have a unified story, because if you're constantly going back down to the building blocks of your story and you're constantly moving them, you're never going to get a house. You're going to get some, broke down hovel that you're constantly remodeling. And that's not the arc of how we do science. We want to be able to have clean and neat stories. And I think
all knowledge humans convey is in stories, essentially, right? There's a beginning, middle, and end. Otherwise, like even a sentence has a beginning, middle, and end. Yeah,
you have to have an arc, because otherwise it's just a meaningless collection of maybes. And we're always thinking about this, because I think that science fundamentally is a discipline of possibility. And there's one interpretation, and
stories have to change over time, right?
Stories have to change because that's just the nature of understanding. As you expand what you see, your story has to change. And I wonder if anybody is ever looking to see for alternative reasons for redshift. And I'm sure that expansion and increases in distance are a huge contributor to redshift. I'm just wondering, is there ever any conversation about the fact that there might maybe be something else?
Basically now, no, because we've been able to study distances to galaxies and take spectra and measure their redshifts for over 100 years now. And people have come up with alternate theories, and they have been repeatedly disproven time and time again. So I wanted to latch on to something you said, which is that like science is a story, and that's true, or it can be true, and that we want a clean story. And we always want a clean story, but that's not what the universe gives us. And in fact, you do need to routinely go back and look at your building blocks, because just because you can build a house that looks clean doesn't mean it's not going to fall apart if your blocks have cracks in them, right? And so, something that I think of a lot when people are convinced that there is some conspiracy in science, or that there is some theory that everybody just accepts, but it might not really be true, is that scientists love nothing more than to discover something new, and that discovery could be proving wrong some well-believed theory. So there is literally zero incentive from a scientist's perspective to go along with some kind of conspiracy, to overlook evidence that says some well-accepted theory is wrong.
Well, it doesn't have to be a conspiracy. I mean, it's happened many times in the history of science, right? That we thought something for sure was the case, and then it just wasn't.
And then new observations come along and disprove it. That's science. That's how science works. That's how we make progress in the world. And that's why you do have to go back and look at your building blocks when you do get more information, because you learn, right? Example I give in my class is that Newton had his ideas about the law of gravitation, right? It's wrong. Einstein's theory of general relativity is more correct. It's the most correct idea of how gravity works that we have now. But you wouldn't actually say that Newton was wrong or that he was an idiot. It's that his theory was incomplete, but it was pretty close at that time.
Overly simplified.
Sure. And it may turn out that there is something, more richer, more complex than Einstein's theory of general relativity that we haven't discovered yet, but we probably wouldn't go around saying Einstein was wrong or he was an idiot. It was just incomplete at that time.
But sometimes the observations aren't sufficient to, the data can stack up, and you can keep tacking on epicycles and explain it with increasingly complex mathematics, and you can be completely wrong but completely precise, and the observations can match very nicely, but you're still dead wrong. And that's really fascinating element that doesn't necessarily involve precision, observation, mathematics, or anything of the like.
Or a conspiracy.
Yeah.
And so, I think that dark matter seems to really fire people up about this, because it does seem like something that's undetectable and something that has been added to models.
Undetectable, but not yet detected.
Right. And so the question is, how long do you keep looking before you start? Because look, what you said about, every scientist wants to find something that will change the arc of the story that's being told is true. But there's also a very natural and to be expected conservatism in science, which demands that you don't knock the entire house down. Nobody wants the whole house to be knocked down, right? And so if there's a different reason for redshift, let's say, then you run into a problem where 100 years of science, of people basically being, we are absolutely dead certain that this is the case, gets unseated. And that's not it's not a conspiracy where people are getting together in dark rooms and they're like, we must prevent anyone from finding out that it's not the case. It's just a question of just not wanting to even think that maybe everything that you've believed your entire career and that you've taught people and that you've put into textbooks and everything else. It's because we know that cognitive dissonance is a problem, right? Like you go and you look into any psychological research and it's writ large that people have a huge tendency to ignore facts that would shatter their belief structures. And scientists are people. They're disciplined and focused people, but
I freaking hate it when someone shatters my worldview. It's like the worst feeling ever.
It is absolutely the worst feeling ever, to the degree that I catch myself refusing regularly to look at things that would
It's hard,
challenge
yeah,
it.
it's hard.
And so I guess it's like the fact that no one is studying that perhaps redshift might have other components to it is alarming, because I'm like, isn't
Well,
that
for example, we were talking to this cosmologist in Canada yesterday.
John Moffat from the Perimeter Institute, which was a wild conversation because he's 90 years old and he's just been working in the field for his whole life.
I don't think he's unusual in that he is trying to come up with new models for the first few moments of the Big Bang that are able to account for some of this new data. I think that's probably a hot research area right now among cosmologists. But he's basically proposing, and I think others are too, that the basic physics at the early moments of the universe was different than the basic physics now. And that doesn't seem any crazier than the basic physics of light at great distances is different than it is in proximity or something like that. I'm not saying it's the case. I'm just like, it doesn't seem more crazy or less crazy. I mean, sorry.
Yeah.
Right, but I mean that's basically a hypothesis, right? You have a hypothesis that maybe light, something changes with light as it travels over distance, and so the way science would work is you'd have to design an experiment that could support or reject your hypothesis. And I would venture to guess that any experiment you could come up with would not support that hypothesis. And I don't think it's that scientists, like you said, we're people, we're trained to not let our minds hide potential truths from us, right? But we are people. But I think that particular aspect of redshift is just something that seems so unlikely at this point based on all the observations.
Well, what's so
that have been
crazy
made
is
to be wrong.
These are like such astronomical distances, right? I don't know how you do a tired light experiment on Earth or any. That's what's so bizarre about this. If you're talking about studying the first few instants of the universe, of all of existence, that's bound to be an interpretive science that relies on abstraction after abstraction of indirect evidence, because you can't do one of those in the lab. You're not going to just make a universe in your laboratory. And I think that maybe it's just such a like the idea of studying distance-related redshift in a laboratory is just mind-boggling. I mean, I guess you could use mirrors maybe or something, but still then it would be indirect, right? Then you're still making an artificial system that people will point to and be like, it's not quite.
What is the closest object that has a redshift?
Yeah, how big of a laboratory do we need?
Beyond the local group, for sure. So Andromeda, the biggest nearest galaxy to our own, is actually blue shifted because we're moving towards each other. So, on the order of probably 10 million light years or something like that.
That's a big laboratory.
But so I want to say about tired light. You guys had actually mentioned that in our pre-interview, and I'd wanted to read more and never got around to it. But like much smarter people than I am have spent time actually working on this and debunking this. And one interesting example that I did see when I was skimming some stuff about this is time dilation. So in our universe, things that are farther away from us because of the expansion of the universe, when you receive light from that object, you are observing, say you're looking at a light curve of something that changes with time. The time axis of that light curve gets stretched by the redshift. It's really 1 plus the redshift. So imagine there's some event that took 10 days in real time. You would observe it to take 100 days if it was coming to you from a redshift of 9, because the time axis gets multiplied by 1 plus 9. So if
this is just a consequence of general relativity.
Yes, and so if there was an object that was not truly that far away because tired light was real, and it was not redshifted due to the expansion of the universe, you would not see that time dilation. But we do see it, and supernova light curves are the easiest one because you can see those very distantly.
But what's so fascinating about that is it's a consequence of a theory that's our best, most precise theory of gravitation right now, right? But if we had like extrapolated Newton's theory, we might come up with things that didn't totally make sense also. And it would just be because we hadn't had a more precise description of that phenomena. And
evidence began to mount that something was wrong with our current cosmological theories. I think you would see more people look at it. And evidence is mounting in one particular area, and people are looking into it. which is the actual expansion rate itself. There's a tension between the expansion rate measured locally and the expansion rate you infer when you study the cosmic microwave background. It's known as the Hubble tension. And so people are trying to say, okay, maybe it's due to an issue with the observations, and plenty of people are working on that. And as time goes by, that has not yet been a conclusive answer. So people are trying to say, okay, how could I actually alter our best idea of how the universe works to accommodate that? And there's one idea, I maybe mentioned this we talked before, called early dark energy, where what if there was a particular time in the early universe where the expansion was a little bit faster and then it slowed down because there was some other kind of dark energy at that time. If you do that, you could reconcile these observations. That does not mean by any means that is what happened, but it's a way you can modify our modern theory of cosmology to fix this particular observational disagreement. So then what you need to do is say, okay, what other observational tests could you make? What else would change that is directly observable if this really did happen in the early universe? And so people are looking into that, and I don't know the answer to it, but that's sort of the next step, right? Before you would say, okay, we're going to replace our standard cosmology, which we call lambda cold dark matter cosmology, with this early dark energy plus lambda CDM, or whatever you may call it. Lots of work would need to be done before you would agree on that.
Can you elaborate a little bit on this time dilation that you can see in supernova?
Mm-hmm. So supernovae, not only are they standard candles in that they have like the same intrinsic luminosity, at least these particular type of supernovae, they have a standard sort of light curve. So their time as the light increases, rises, and then falls off there's a standard basically cadence, right? So if you look at more distant supernovae, you will see that light curve get stretched out in time due to this time dilation effect.
Sorry, what are the axes of that curve?
Sorry, brightness versus time.
Got it.
And time is measured by
the observer. So just as I'm studying this object, I'm observing it, let's say I'm taking a picture every 10 minutes. I would have a time axis on my light curve plot.
I guess what I'm sticking on is I'm surprised that the change in the light intensity of a supernova is, you're saying that how long do you have to watch it for in order to generate a light curve like this?
Several days. So in the several days or weeks.
Interesting.
And the reason why these particular type of supernovae are good sort of standardizable objects is because they are all the same event. They're a white dwarf exploding when it hits a particular mass of 1.4 times the mass of the sun. And so they all explode at the same mass through the same physical mechanism. So they're all roughly the same brightness. Mm-hmm. And I say roughly because there's some evidence that the brightness can change a bit based on the metallicity of the object, the chemical composition. But that's actually something you can measure and correct for.
Mm. I meant to ask, we had an astrophysicist on the show on Monday, and I meant to ask him why these white dwarfs, they're supposed to be at the end of their life, right? As I understand it. And why are they so bright, or why are they white? Usually we think of hot things as white on Earth, right? Like white hot. But these are
hot.
They are hot. Okay.
They're like 30,000 degrees. Yeah. So they're the leftover cores of a star.
They're like hotter than the star. They're hotter than the giant. I see.
That's right. That's right. Yeah.
Cool. So I want to say one last thing about this. I was really interested in these tired light things, and I studied them a bit about 2 years ago. And I also was deeply dissatisfied with all of the explanations that I found. And but I still maintain that doesn't, maybe it's not tired light at all, but there's something else that we don't know about. And that's really just the way science works, I guess, is that we have to proceed until we have a better version of what could be causing whatever. I mean,
I think somebody would have to be motivated by there's some kind of observation, something that's been seen that really doesn't make redshift due to expansion make sense to me. So I'm going to come up with a hypothesis about what else it could be and design an observation to test it. And I think that first step has just not happened, right? There's no dissonance anywhere with using expansion as the definition of redshift. Now, when we talked about that Hubble tension, now there's increasing dissonance there, and you see people motivated to actually study that and come up with alternative ideas. And maybe as measurements get more precise, maybe someday we'll need to revise how we define redshift or what it means.
I think like the better we understand what
skeptical that would happen.
The better we understand what light is too, in terms of, material atomic understanding of nature and really what's going on at the atom and so on and so forth. I think that could also lead to some insight down the road.
Yeah, I mean, I think we understand light pretty well. One thing we don't understand is what dark energy is. Why is it there? Why is it, why is there this thing in the universe that's causing the expansion to accelerate? And, at some point, I have no doubt humanity will have a much better understanding of that phenomenon. And maybe that, you will then have a better understanding of space-time, which is the medium through which the photons are traveling. And maybe that is a way in which you would have a better understanding of redshift itself.
Yeah. I mean, we have like fantastic descriptions of how light behaves, but in terms of like, I'm a material scientist by training. That's what I did my PhD in. And in terms of what actually is physically going on with the atom, like its actual material structure and all of this it's very schematized. The atom is basically a wiring diagram right now. We have elegant mathematics that are very predictive, very powerful, but we don't really like have this, you can't really like shrink yourself and imagine what's going on down there yet. And I wonder as that conception, that theoretical material science develops, I wonder if we'll have better insight into what's actually happening during light and atomic orbital transitions and all of this process.
That was something that Moffat said that was really surprising to me, because we were talking about gravity with him. He has a modified theory of gravity that does away with dark matter. And we asked him, well, what is gravity? And he's like, well, that's not a question that physics asks. And I think he's right, because, you ask people and they look at you like you're an idiot. Like, what do you, who, like, it's just like, well, there's a graviton. Like,
there's great equations.
There's great equations. Like, we don't occupy ourselves with the question of what is gravity, what is electricity, what is light in physics.
We occupy ourselves with how they happen in physics and what the generalizable pattern of that is. And
what can we build out of it? Yeah, but it's the question of, well, okay, so what does the math mean? What does the math describe?
I propose a new academic department to study these sort of questions, because the philosophers don't want to touch it, the physicists don't want to touch it. It's like completely orphaned discipline.
Yeah, like I said, I think people have to be motivated to want to study something. And so you need to have some indication that a line of research is going to be fruitful. Otherwise, you're going back to study all of the building blocks, and many of them are quite well constructed. And I don't know. I was going to say I should look up his website and see what he has to say. But if there's an alternative theory of dark matter, it needs to explain the bullet cluster. That's the easiest observation that rules out a lot of modified Newtonian dynamics dark matter theories.
We've been talking about doing episodes where we have two people on that are very, very far more educated than we are in disciplines. And so if you look at his work and you like what he does, he loves to talk. I think he has the time to talk as well. Yeah. And so it would be cool to get people together to talk about this stuff in a way that's, far over our heads and see what they can come up with.
Yeah. So what are some of the observations that are coming back that are really shaking things up? What's going on out there at the frontier of what's being observed? I saw some really crazy, we're talking about really short amount of time to get fully formed galaxies, This is just fascinating. Couple of 100 million years. This is like the age of the seafloor on Earth, and you got to build a whole galaxy in that amount of time. What does that look like?
Yeah, so that has been the most interesting thing, I think, that's come out of JWST so far. We're finding galaxies very early on. There have been some reports that there are galaxies that are more massive than one might expect, to the point where it just seems really hard with our current understanding of the universe, our current theory, this lambda CDM theory I mentioned. But I think everybody just needs to be patient, because I mentioned the very first thing we talked about was this calibration of the telescope, and it's still very much a work in progress. And as you change that calibration, we're talking about at the tens of percent levels, that can really change basically the color that a galaxy is in the image. And the color is what we use to measure both the distance and infer quantities like luminosity or stellar mass. And so as this calibration shifts around, both of those quantities can change. So for example, there was a paper claiming these incredibly massive galaxies, like as massive as the Milky Way, existing 500 million years after the Big Bang. And I would be really, really, really surprised if that stands the test of time. And not that anything wrong was done in the analysis. They took the ground-based calibration that was available, made some measurements, and that's what they got. But as the calibration has changed, it's changing in a way that would make the galaxies appear less massive. And, like by a factor of 10, based on a test that we ran. And if you can change that so much with this like pretty slight change in calibration, I think everybody should sort of like hold their horses trying to rewrite modern cosmology until the telescope is like fully calibrated. And that's not shade on JWST. It was well known that calibration was going to take the entire first cycle, and that people should be careful. So I think it's taken folks, and myself included, a little while to realize how important this is. And that's not a reason to wait and not do science now, but we just need to keep in mind, okay, we might have this uncertainty of, 10%, 20%, whatever it is. What can we say that's kind of invariant to that level of uncertainty? And maybe we write those topics now. And what do we really need to get to like percent level calibration? And we should wait, 6 months, whatever it takes before we have that.
And so you expect it to be available within 6 months or so?
They're observing these stars, these standard stars throughout the year. But I think the calibration files will get updated like pretty routinely. So it'll be sort of a slow improvement throughout, the next, because we're sort of, what month are we in? Cycle 1 started July 1st. So we're sort of 2 months into cycle 1. So 10 months left in the year.
Do you think are there new proposals that are going to go out once it's calibrated? Because obviously if it is true that, things need to be reconsidered in cosmology, it seems like there's going to be a huge feeding frenzy.
Yeah, the next proposal deadline is the end of January. So we sort of have that long to learn as much as we can to then decide how do we want to use year 2 of the telescope.
What are some of your plans?
We want to get spectra of all of these really distant galaxies we're finding, even if, it's at redshift 12 instead of 13, or it's, 50% the mass of the Milky Way instead of the mass of the Milky Way, whatever. They're all interesting. And so the NIRSpec instrument is capable of taking spectra of 100 galaxies at a time. It's incredibly powerful. We've never had anything in space like that before. And so that's a very, very obvious follow-up to this year's project, is to do a big spectroscopic survey of everything that we've discovered.
Are you expecting to find that they'll have anomalous spectra? Like, because I can imagine, let's say the galaxies form, the shapes form very early and they're luminous, but their composition is not what you would expect.
Yeah, so certainly that is a very exciting thing that we will discuss in the proposal, is that they could have very anomalous spectra. They could be very, very different from galaxies today. And we're sort of limited by our imagination. So when I say anomalous, what I really mean is, well, after the Big Bang, you only had hydrogen and helium. And if you're forming galaxies very early, they probably are predominantly hydrogen and helium, not very many heavy elements, because those need stars to form. And if you were to form galaxies out of that, how might their spectra look? Here's how we could actually observationally test that. That would be sort of the structure of the proposal. And then you take the observation and maybe you see something completely unexpected and anomalous, and then you have to figure out what it actually means. That's the exciting part.
Yeah, absolutely.
How do you, all right, so when we're working in where I come from, I've done work in a lot of different fields. Usually we have to justify the technological application of our work. How is this going to make life on Earth better?
Especially when you're writing Department of Defense grants.
Yeah, well, yeah, I mean, we did write a Department of Defense grant, even though we wanted to ask some very, very different questions about nature, but that was where the funding was, right? So what's it like when you write astronomy grants? How do you have to justify it in terms of being practicable, or?
Yeah, because that's the same thing in biology too. You know, you're like, this will help us cure this disease, and everybody in the
Right,
lab
right.
is just like, oh my God.
No, this is basic research, right? So it does not have to be practical. And if you demanded all research be practical, then I think you would really limit the pace of scientific discovery. There are numerous examples of how the development of technology for astronomical observatories has benefited everyday life. Like Wi-Fi has its origins back to like some radio telescopes, and their websites. I don't have like all the information in my head, but that's there. But that's not why we do it, right? We do it because we want to understand where we came from, and it's a luxury. And I'll be the first to admit that we're not curing cancer out there, right? But it's almost like science as an art form. We have the ability technologically to take these amazing images and to learn about the entire structure of the entire universe. We can barely even get our human bodies off this planet, and we may never get humans to another star that's pretty close by, 4 light years away. Yet we can actually study what is happening in galaxies billions of light years away. We can measure a detailed history of the universe and explain so much just with a telescope that's, the size of a tennis court, that we managed to decide to spend a tiny fraction of, the world's money on to put into space.
I think that's very therapeutic for civilization at large in some sense.
Right.
It's historically been the case too. If you think about, at least in the indigenous cultures of the Americas, astronomy was a highly regarded class or astronomers were a highly regarded class. I think they overlapped with the priest class and to some extent with the ruling class, because they were able to give some sense of place for humans on Earth. Really give them a meaning in a cosmic sense. I mean, cosmology, when you really think about what the word means, it's really about humans' place in the universe. And that's something that you can't directly pin to a technology necessarily, but it does offer some value, I would say, a really important value.
Yeah, well, and that's a value for everybody, right? Is an inspiration. But another, in addition to technology that I mentioned, is astronomy can really be a gateway drug into the sciences. Astronomy is really easy to enjoy, and so it helps get people interested in science, and some of them stay interested in astronomy and become astronomers, but some of them might go be engineers, or might go be biochemists or whatever, doing these really technical roles that help benefit society. And so when you look at like an absolute dollar value, so $10 billion, that was the cost of the telescope, you might think, how many problems on Earth could we solve with $10 billion? Well, a lot, although you only get the money once. Depending on the audience, I might not talk about this too much, but take a look at our national defense budget. It's like $500+ billion every year, right? So if you
that we know of,
right? If you want to talk about, sort of priorities in national spending, you can't just pick and choose and say, oh, this, telescope, what can we do with that? You should really look at everything. NASA's budget in general is paltry. I was talking about that in my class yesterday. It's 0.5% of the national budget, and a lot of that goes to the crewed spaceflight program. So science gets a tiny fraction of that. So I think it's certainly debatable, but I think that debate should encompass all federal spending and not just focus on this one thing that sounds egregious when you say that dollar value. But I think the telescope is working so remarkably well. And it's going to work for 10, 15, maybe even 20 years. And so I think we're certainly going to get our money's worth out of it. And if you take the cost of the Hubble Space Telescope and move them to $20, it's actually pretty similar. And this telescope is way more powerful than Hubble. So I think it's a privileged position to say this, but I think we're getting our money's worth.
I think it matters to people, even if they can't put words to it. It's just it's very important to everyone. I think that's why it appeals to introductory students so well. There's just something ineffable. Everybody walks out and looks at the stars and it's like, what the heck? It's just it's a natural thing, natural feeling that's occurred to people for ages. The last thing I wanted to ask you is, what's the plans for the next gen of telescopes? Are you working on that, or?
Yeah, so there's sort of a near future and a far future. So NASA's next sort of moderately big observatory, it's not quite this big, is called the Nancy Grace Roman Space Telescope, named after astronomer Nancy Grace Roman, who was called the mother of Hubble. She helped get the Hubble Space Telescope off the ground. And that is actually, it's an interesting story about that telescope. It is a former spy telescope. So this was 8 years ago. The National Reconnaissance Office came to NASA and was like, hey, we've got 2 Hubble-class telescopes in a hangar that we're not using. Would you like one? And NASA was already planning a telescope that was to have like a really wide area camera to do these really big surveys. Both Hubble and JWST, their cameras are really narrow, so they can only see a small area of sky. And the telescope was actually going to be small. It was going to be like 1.5 meter in diameter mirror, but Hubble was 2.4, and that's what this one sitting in a hangar was. And so we sort of got an upgrade to this mission. So it's basically a Hubble-sized telescope, but the camera has a coverage, an area coverage 100 times larger than Hubble. So in that particular aspect, it's 100 times more powerful than Hubble. It doesn't go as far into the infrared as JWST, so it's kind of limited in that way. It's 2.4 meters, so it's limited in that way, but it's going to do these enormous surveys. And that's one thing that's so great that JWST is going to be around for a while, is you really should have done like this Roman Space Telescope first to do these huge surveys, find all these weird, interesting objects that you can then study in more detail with JWST. But this is slated to launch, I believe, in 2027. And so it's more or less been given full approval. Things are happening, being constructed, and big surveys to study the nature of dark matter. That's a big one. The nature of dark energy by measuring the expansion of the universe more precisely. And what I'm interested in, huge surveys to find really rare massive galaxies that, you know, you'd have to get really lucky to hit on with a JWST observation, but we'll find a lot of them in this telescope, and then you can go follow them up with JWST or with the next generation of really big ground-based telescopes, which is in parallel to NASA. There are several sort of 25 to 40 meter diameter telescopes being planned. The one that we are most involved in here in Texas is the Giant Magellan Telescope. It's going to be a 25 meter diameter telescope being built in Chile. Wow. And it's a consortium of universities, some in the US, UT Austin, Carnegie Observatories, University of Arizona, Harvard, a few others, and some other nations, Australia, Korea, are all involved. And it's being constructed right now. It's going to take a while. First light is sort of 2030 or so. The Europeans are building the European Extremely Large Telescope. It's a 39 meter diameter telescope that's also going to be in Chile. And that will actually probably get on sky a bit earlier, maybe late 2020s. And then there's a design being led by Caltech and University of California and China, Canada, a few other countries, called the 30 meter telescope. That is a little bit of hiatus because it was originally going to be built on Mauna Kea in Hawaii. And there's a lot of pushback from native Hawaiian astronomers that don't want new construction on their mountain. So they're sort of trying to decide whether they will build it there, whether they will move it somewhere else, or whether they will just not build it at all.
Is it a serious problem having the atmosphere to look through on these things?
So you would always opt for no atmosphere other than atmosphere, but there are significant advantages. So for example, the Giant Magellan Telescope, when all is said and done, will probably cost about $1.5 billion. So significantly cheaper than JWST with a significantly larger mirror. And because you can like drive to it, you can upgrade it all the time, right? Whereas JWST, we cannot upgrade at all. And yes, you have to look through the atmosphere. And there are some aspects of that you can get around. It's a technique known as adaptive optics, where you can try and remove some of the atmospheric turbulence. So it's very complementary. So you would never design a ground-based telescope to do the same thing a space-based telescope is already doing. But you can build them bigger on the ground and build better, more complex instruments and upgrade them.
Are there rumblings of a new space telescope to follow up the JWST?
So there were lots of designs, and astronomy does this once a decade process called a decadal review, where people submit their best ideas, and the National Academy of Sciences convenes a bunch of committees to basically rank them. And then they hand that to NSF and NASA and say, here are your priorities. And then there's a pretty good tradition in this country of NASA and the NSF work from those priorities and say, okay, we have this amount of money, we can fund the top 3 things. And so there were 4 sort of big space telescope designs pitched. And the National Academy basically mashed a couple of them together and came up with sort of a JWST-sized UV optical telescope. So as soon as Hubble dies, whenever that is, we won't have the ability to do ultraviolet astronomy anymore. The atmosphere completely absorbs UV light, which is great because it gives us cancer. And so you need to do that from space, and soon we won't have that capability. And so there are lots of reasons why you want to study those wavelengths of light. And so that's sort of the next big mission that would be in development, which is going to be cool. There was a submission for a 15-meter diameter telescope called LUVOIR, the Large UV Optical Infrared Telescope that I was rooting for. And I think they decided that it would just be way too expensive, which is too bad because that would have been really cool.
Yeah, this is cool. One of the things I love about astronomy is that you can continually improve these instruments and get better and better resolution. And it's like you can build a better electron microscope, but it's basically still an electron microscope. And yeah, I find this really exciting because as time goes on, we can definitely expect to learn more. We're going to be able to see better and further, perhaps. And yeah, it's really exciting.
Yeah, definitely.
Well, I don't want to take any more of your time today. It's been really fun talking to you. I've learned a lot. And yeah, I just want to thank you for coming on.
Yeah, it's been really great. Thank you both. You ask a lot of really interesting, deep questions, which are hard to answer sometimes.
We're curious.
And it's an amazing opportunity to get people on the show who think so deeply and abidingly about the farthest reaches of human understanding. And so it's a real pleasure to be able to talk to you and to get your perspective on the place of humans in the cosmos. It's very cool. So thank you.
Yeah, thank you.
All right. We'll catch up with you down the road. Have a great rest of your day.
It sounds great. Enjoy the Pacific Northwest. I miss it. I love it.
Yeah. Take care.
Yeah, I'll see you later. Bye.